Welcome students in Excellence Classes Way of Learning. Today we are going to discuss real number part 2. In previous class we discussed about the Euclid's division algorithm and Euclid's division lemma with some examples. Now today let's start exercise 1.1. Here exercise 1.1 is on your screen. If you want, take a screenshot. Okay? So here exercise 1.1. Question number 1. Use Euclid's division algorithm to find the HCF of, here first, 135 and 225. First we have to choose greater number between these two, that is 225. So we have dividend is equals to 225 and divisor is equals to 135. Okay, by using Euclid's division algorithm, you know that dividend 225 is equals to divisor 135 into quotient plus remainder. To find the quotient and remainder, we have to use long division. So here 1, here 135, here 9, here 0. Here we got quotient 1 and remainder 90. Here 90 is does not equals to 0. Here 90 is does not equals to 0. So again we use Euclid's division algorithm here. So 135 is equals to 90 into quotient plus remainder. Again here 135, here 1, here 90, here we got 45. 1 quotient and 45 remainder. Here 45 is does not equals to 0. So again here 90, 45 to the 90, here we got remainder 0. Okay, here 90 is equals to 45 into quotient 2 plus remainder 0. Here we got remainder 0. So 45 is required HCF. Okay students, hence HCF of 135 and 225 is 45. Okay, now question number 2. $196 and 38,220. Here dividend is equals to 38,220 and divisor is equals to 196. Okay students, here by using Euclid's division algorithm, we have dividend 38,220 is equals to divisor 196 into quotient plus remainder. So here we use long division to find quotient and remainder. Here 1, here 196, here we got 6, 8, here 1, here 2, here 196 9s are 1764, here we got 8, here 9, and here 0. 196 into 5 is equals to 980. Here we got remainder 0. Okay. Here quotient 195. Here remainder 0. Here remainder is 0. So required HCF is 196. Okay students. Hence HCF of 196 and 38,220 is 196. Okay students. Here question number 3. 867 and 255. Here 867 is dividend. 867 is dividend and 255 is divisor. Okay. So here by using Euclid's division algorithm we have dividend 867 is equals to divisor 255 into quotient plus remainder. So here 867 divided by 255, here 3, here 765, here we got 2, 0, here 1, here we got quotient 3 and remainder 102. 102 is does not equals to 0. So again we apply Euclid's division algorithm. Here 255 is equals to 102 into quotient plus remainder. So here 255, here 2, here 204. Here we got 1, here 5, here quotient 2 and remainder 51. Again 51 is does not equals to 0. So again we apply Euclid division algorithm. So here 102, 51 into 2 is equals to 102. So here we got remainder 0. So here 102 is equals to 51 into quotient 2 plus remainder 0. Here we got remainder 0. So required HCF is 51. Okay students. Hence HCF of 867 and 255 is 51. Okay. Now question number 2. Show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5 where q is some integer. Okay. All of you know that Euclid's division lemma. Euclid's division lemma here a is equals to bq plus r. You know that. Okay. A is equals to bq plus r where r is greater or equals to 0 and less than b. Okay. Now we are going to solve this question. Okay. Let a be any positive integer and b is equals to 6. Let a be any positive integer and b is equals to 6. Then by Euclid's division lemma a is equals to 6q plus r because here b is equals to 6. Okay. A is equals to 6q plus r for some integer q is greater equals to 0 and where r is greater equals to 0 and less than b. Okay, so here the possible remainders are 0, 1, 2, 3, 4 or 5. Okay students, that is a can be 6q or 6q plus 1. Okay, 6q plus 1 or 6q plus 2 or 6q plus 3 or 6q plus 4 or 6q plus 5, where q is the quotient, Okay, if a is equals to 6q or 6q plus 2 or 6q plus 4, then a is an even integer. Okay, if a is equals to 6q or 6q plus 2 or 6q plus 4, then a is an even integer. Also, an integer can be either even or odd. Can be even or odd. Therefore, any odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Okay students, let us revise. You know very well a is equals to bq plus r, where r is greater equals to 0 and less than b. Let a be any positive integer and b is equal to 6. Here a is equals to 6q plus r. We have b is equals to 6, so possible remainders are, here b is equals to 6, so here possible remainders are 0, 1, 2, 3, 4, 5. That is, a can be 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4, 6q plus 5, where q is the quotient. If a is equals to 6q, 6q plus 2, 6q plus 4, then a is an even integer. Therefore, any odd integer is of the form 6q plus 1, 6q plus 3, 6q plus 5, where q is some integer. Okay. Now question number 3. An army contingent of 616 members is to march behind an army band of 32 members in parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? Okay. To find the maximum number of columns, we have to find the HCF. We have to find the HCF of 616 and 32. Okay. So here, by using Euclid's division lemma, we have dividend 616 and divisor 32. So here dividend 616 is equals to divisor 32 into quotient plus remainder. Here 616 divided by 32. Here 1, here 32, here 9, here 2, here 6, here 9, here 288, here we got remainder 8. Here quotient 19 and remainder 8. It is does not equals to 0. So again we apply Euclid division lemma. Here 32 is equals to 8 into quotient find करेंगे अब. Here 32, here 4, here 32, here we got remainder 0. Here quotient 4 plus remainder 0. Here we got remainder 0. So our SCF is 8. Okay students. Here our SCF is 8. Hence the maximum number of columns is 8. Here is a key point to solving these type of problems. Listen carefully students. For maximum number, as in this question, we find the SCF, otherwise for minimum we find LCM. Okay students. Now question number 4. Use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay. Let x be any positive integer. Let x be any positive integer, then it is of the form 3q, 3q plus 1 or 3q plus 2. Now we have to prove that the square of each of these can be written in the form of 3m or 3m plus 1. So here 3q whole square is equals to 9q square. Here 3q square is equals to 3m, where m is equals to 3q square. Okay. Now 3q plus 1 whole square. Using identity a plus b whole square, we have 3q whole square plus 2 into 3q into 1 plus 1 square. Here 9q square plus 6q plus 1. Here taking 3 as common from starting two terms, we have 3 bracket 3q square plus 2q bracket close plus 1 is equals to 3m plus 1, where m is equals to 3q square plus 2q. Okay. Now 3q plus 2. Here 3q plus 2 whole square. Again using identity a plus b whole square, we have 3q whole square plus 2 into 3q into 2 plus 2 square. Okay. Here 9q square plus 12q plus 4. Here 9q square plus 12q. Here 4 can be written as 3 plus 1. Here taken 3 as common from starting 3 terms. So we have 3 bracket 3q square plus 4q plus 1 bracket close plus 1 is equals to 3m plus 1, where m is equals to 3q square plus 4q plus 1. Okay students. Square of the first positive integer is in the form of 3m, second in the form of 3m plus 1, and third is also in the form of 3m plus 1. Okay, clear? Now question number 5. Use Euclid's division lemma to show that the cube of any positive integer is either of the form 9q, 9q plus 1 or 9q plus 8. Let x be any positive integer then it is of the form 3m, 3m plus 1 or 3m plus 2. Now we have to prove that the cube of each of these can be rewritten in the form 9q, 9q plus 1 or 9q plus 8. So now 3m whole cube is equals to 27m cube is equals to 9 into 3m cube is equals to 9q, where q is equals to 3m cube. Okay, so here 3m plus 1 whole cube. Using identity a plus b whole cube, we have 3m whole cube plus 3 into 3m whole square into 1 plus 3 into 3m into 1 square plus 1 cube. Okay, is equals to 27m cube plus 27m square plus 9m plus 1. Taking 9 as common from starting 3 terms, so we have 9 bracket 3m cube plus 3m square plus m bracket close plus 1 is equals to 9q plus 1, where q is equals to 3m cube plus 3m square plus m. Okay, so here 3m plus 2, here 3m plus 2 whole cube. Again using identity a plus b whole cube, so we have 3m whole cube plus 3 into 3m whole square into 2 plus 3 into 3m into 2 square plus 2 cube. Okay, so here 27m cube plus 54m square plus 36m plus 8. Okay, taking 9 as common from starting 3 terms, we have 9 in bracket 3m cube plus 6m square plus 4m bracket close plus 8 is equals to 9q plus 8, where q is equals to 3m cube plus 6m square plus 4m. Okay, here cube of first positive integer is in the form of 9q, second in the form of 9q plus 1, and third is in the form of 9q plus 8. Okay students, exercise complete.